So it's a very optimistic view. I don't know how well I did, but let me give you a little bit of background of me. I started out as a chemical engineer, then became a computational chemist. So I've been living really on the edge of science and computing, ranging from doing science to actually developing codes to run on high-performance supercomputers. So quantum computing is just, to me, another tool, a potential tool for us to actually do science with chemistry applications. So I'm located at Berkeley Lab, which means I'm just above the hill from UC Berkeley, where there's actually also a lot of work being done on quantum computing. There's actually hardware being developed there that is very similar to what Google is talking about here. So let me start with a very simple question. Why quantum chemistry on quantum computers? That title should give you enough. Quantum chemistry or computational chemistry uses at heart the quantum algorithms, the quantum mechanics that physics brings to the quantum computers. So if you really look at it, the fit for quantum chemistry on quantum computers should be very natural. Now I'll show you that that is not the perfect solution yet, but eventually we'll get there. So what can we do potentially then if we use quantum computers and quantum chemistry together? We can go from using fundamental theories and developing fundamental understanding to control. So think of very simply of being able to control the pathways in biosystems, developing better catalysts, or even developing better materials, and eventually potentially even develop better materials that might be used for the next generation quantum computers. So give you a few vignettes or a few examples of what we are thinking about when it comes to trying to use quantum simulation and quantum computers together. So one of the first ones that would be very natural is starting to look at the discovery of guiding principles of catalytic activity. It could be a very wide range of research that you start to look at. Of course, everybody, if they ever read anything about quantum computing and heard about chemistry application, the first thing they will read is the one that's on the, for you guys on the right side, is nature's answer to the Haber process, right? We all want to break N2 and make NH3, and nature can do this at room temperature and 1 atmosphere, and we have to use a lot of energy to actually do this experimentally. Those problems right now we cannot easily compute with quantum chemistry applications. Actually, in reality, we cannot do it right at this point in time. Other things that we have to look at is photoexcitation, photo-induced excitation processes, coupling of electron and photon transport processes, to really start to look at the whole end-to-end catalysis process. Realistically, if you want to do this, we probably need in the order of 100-ish ideal qubits. And you just heard already this morning, 100 ideal qubits does not mean you need 100 qubits. You need a lot more to get to that level of computation. You already heard a little bit about this too. So in reality, strongly correlated materials means we are looking at how electrons correlate, and that happens in materials, that happens in chemistry. So to me, chemistry and materials is a little bit of a fuzzy line sometimes. So, but if you really look at the electron correlation in materials, we use it every day. We use it in MRIs. We would like to be able to have superconducting wires to move our currents, because right now we lose a lot of energy in the transmission lines. Battery materials are all driven by electron correlation processes. So how can we make better materials? How can we design better batteries that store more energy and actually get more bang for your buck for a business? Problem is, these are very hard to compute right now on classical computers, simply because the computational complexity of the problem. Chemistry, it's very interesting that there's a lot of analogies there. I already mentioned the enzyme earlier. There is similar systems like the iron-sulfur system, which is a combination of irons and sulfurs, which are very hard to compute. People use approximate methods right now to try and get a good description and a good understanding of that process, but it's a very challenging problem. A lot of people are working on molecular switches. So a lot of these processes are driven by electron correlation again. So if you want to design a better molecular switch, you need to understand the electron correlation and be able to predict what that might be. So I mentioned already now a couple of times electron correlation. So in reality, electron correlation is well described by the quantum mechanics that we have. So the Schrödinger equation, which is, or the Dirac equation, and this is actually a quote by Dirac, that equation effectively describes the electron correlation between all the electrons in a system. The theory is there, but it's just hard to compute. So why is it hard to compute? Well, we have lots of electrons that we put in different orbitals, but we can orient them or we can stack them in one kind of orientation or one kind of distribution, but that's only one of many. If you want to solve this exactly, you have to consider all the different combinations of how you order or place those electrons in those different orbitals. And that's where the problem comes in, because then it becomes a computationally exponential problem. And you can do the math very quickly, and you'll see very quickly for even a small system, which is about in the order of 100 orbitals and 80 electrons, you're getting to problem sizes that are in the 10 to the 160, which is way larger than the particles in the universe. So quantum computing hopefully can get us to start try and tackle those kind of problems. We're talking about, again, about 100-ish perfect ideal qubits to be able to try and tackle these kinds of problems. So why do we actually worry about quantum computing? If you would know about Berkeley National Lab, you would know that we are actually having a very large supercomputer ourselves. It's about 15 petaflops right now. We're not the largest. There's 2 labs in the DOE system that have larger. They are in the hundreds, and soon will be in the 250 petaflops. But reality is, if you go and look anywhere on this line, we heard Moore's law is dead. Moore's law is not dead yet. We will actually have an exaflop in 2021. The hardware pathway seems to be there to get there. But what does that give us? That gives us a factor of 10 performance over what we have now. For an exponential problem, that doesn't do you much. Some of our computational complexities are in the order of 10 to the 6th. 10 to the 6th with a 10 performance increase allows us to go to a problem that is maybe 1 times bigger. That is not going to help us if we really want to tackle the large, complex science problems and fundamental science issues that underlie a lot of the physical processes that are used for any process in industry. So what do you do if you don't have the tools to do computational chemistry on supercomputers? You start looking for the alternative approaches. So quantum computing is one. If you look around, a lot of people are working right now on machine learning, deep learning, actually also for chemistry and materials, because there is also a very nice fit to try and model these kinds of systems. What's really interesting is that people are also starting to look at combining potentially the machine learning and quantum computing together to solve the problems. So this person has been up here already a couple of times, but really the driving force of the idea of trying to do quantum chemistry and quantum computers came indeed from Feynman, who said that, hey, reality with an exponential problem, simulating a quantum system on a classical computer is in the best way, a very inefficient way to do it. So his idea was to actually use quantum computers as quantum simulators. So they are really trying to take a system, put it in a state, and just evolve it over time and look at what happens with that system. Now we have taken a lot of other approaches. We have started to use digital computing approaches and apply conventional digital computing approaches to some extent to quantum computers now too. So there is a couple of different flavors of quantum computing that are being used for quantum chemistry. They are a great match, as I mentioned already, and if we can get to the qubits that we need, I think there is definitely a chance for quantum chemistry to revolutionize that field. And there has been a lot of work done. Theory and algorithmic work has been done already since 2000. And the first demonstrations were about 7 years ago. So there is definitely a way to use chemistry to do use quantum computers to do quantum chemistry. And this is also why you see a lot of the businesses that develop quantum computers take this one on. Again, it's a perfect match. So why wouldn't we use that kind of a technology and that kind of a theory together? There's also a lot of work that has been done more recently, in I would say the last 10 years also, on algorithmic development. And a lot of this actually has been done in the Google group, where they have been able to reduce the prefactors and the complexity of the algorithms so that we can actually compute these kinds of systems on quantum computers. Some work that we have been doing actually is also looking at how we potentially could do something with quantum errors. And what we've been finding out so far, that we can actually use some extra measurements, and I'll get to that a little bit more, to maybe hide some or kind of average out or whatever. We really don't have a fundamental understanding yet how. We're able to reduce the errors of some of our calculations. So I won't go into details here. Qubits, we mentioned the different types of technologies has been mentioned already. There's lots of companies that we can work with, but I should say that it's not just companies that are actually developing these kinds of systems. Everything that's driven on all of these systems is driven by electron spins, so we are looking for spins up and down. So there's lots of ways to generate them, and they have been doing that in various levels of success. So what is Berkeley Laboratory doing on quantum computing then? We actually recently, literally this year, got funded after a couple of years of working on this internally to actually, by the Department of Energy, to do a lot of work on quantum computing in the next 5 years. So we actually have 2 programs that are funded. One is a testbed, which we call Aqueous, that is run by my partner, Jonathan Carter at the lab. And I run a different program called the Quantum Algorithms team that is focused on really developing algorithms and software that can run on these kind of architectures. So the hardware that we're developing is really in collaboration with the Nanoelectronics Lab at UC Berkeley. So they're using a very similar technology as what was talked about earlier with Google. We're using superconducting qubits. What we have right now in the lab, and we are actually doing experiments on, is an 8-qubit ring. So that allows us to not have to go all the way to the end if we want to have coupling between the neighbors at the end. And we're actually looking at topologies too. The key part with all of this is we want to reduce the number of operations we have to do in serial. To do this is to build as much complexity in the network that we can have. And this is no different from conventional computing networks. If you need to connect between processes on a conventional piece of hardware, you can do that in a ring, or you can do this in toruses or higher dimensional networks. And I would expect us as quantum computing, as the quantum computing field, to also start pushing those boundaries to see how far we can get on the connectivity, because that allows us to go and do the operations faster and more efficiently. So in conjunction with the hardware, we're developing also a lot of the underlying algorithms and computer science and applied math. And as you can see, it's an interesting team. If you look at on the top, we have a hardware team that we're working with. We have really applied mathematicians that have never worked with quantum computers, that are learning about quantum computing to understand how they can actually help advance this field. It's the same with computer science. A lot of this is actually circuit scheduling, circuit compilation. Is there work that we can benefit from the conventional architectures and the conventional developments that we can use in developing better quantum algorithms? So our focus on quantum algorithms is actually twofold: dynamics and machine learning. For us, the hardware roadmap is really to get to about, hopefully in the next couple of years, 64 qubits. But we're really trying to do not just building hardware. We're working very close with science and trying to find ways to actually utilize these architectures for different science fields. So we do a lot of software design and algorithm development, and also a lot of characterization in the long run to try and really help push the boundary and the frontiers forward for quantum computing. As mentioned earlier, there is a very interesting trade-off for us if we develop our algorithms in quantum computing. If we want to use it for scientific discovery, well, yeah, one, it's the number of qubits. Two, it's the coherence, the fidelity, or better said, how well can we do our operations. But another problem, of course, is also information extraction. Because, hey, you can put exponential amounts of data in and pull exponential amounts of data out, but both sides of those equation then make it exponentially hard. So you can only put in a subset of your information. You have to start somewhere with a subset of information, and you can only pull out a subset of your information. Otherwise, it will take you forever to get there. And the challenge is really coherence time, operation speed, and the errors, and especially the 2-qubit errors, which is definitely something that is a challenge we see also at Berkeley hardware. So this was already mentioned a couple of times. Also, the best way right now forward is to look at hybrid approaches. So use the strength of all available tools. Classical computers and the quantum computers. Actually, if you really think about some of this, and we can take that as a completely offline discussion, you might actually use a quantum computer and a quantum computer potentially, for example, an annealer with a superconducting qubit quantum computer to do two different components of your algorithm. So the variation quantum eigensolver is really the workhorse that we're using. This is work that really was done in the Harvard group that is part of our team. So we take the strength of the quantum algorithm and we take the strength of a conventional architecture. The strength of a conventional architecture is it can sum numbers. That is something that a quantum computer really is not so good at. The other part of a classical algorithm right now that we do is effectively a minimization, and that potentially we could lay out to a different piece, quantum hardware. And that's really the challenge of this algorithm, the quantum variation quantum eigensolver. You need to do a stochastic optimization. If you do not have a good guess as to where your solution is, you need to sample a multidimensional space. Well, let's say you have 50 qubits. So that means you have to start sampling a 50-dimensional space. That's not that trivial anymore. Even the Argonne fellows that we have in our team working on stochastic optimization are worried about those kind of things. Well, maybe a stochastic approach using a quantum annealer might be a way to actually potentially do these stochastic optimizations at the same time. So there's interesting things you can start thinking about when you have an algorithm and have pieces that are having different needs in the different components of the algorithm. So I mentioned we have been working a little bit on quantum subspace expansion. The reason we started this was actually very simple. Everybody's done H2, but we are really interested in more of the chemistry and physics, and most of the chemistry and physics happens at the excited states. So when you look at quantum algorithms, quantum chemistry algorithms, I should say, a lot of approaches we use is actually use expansions. We do a response, we do a linear response, we do an excitation, we do a perturbation. We can actually use those techniques and actually combine that with some extra measurements and then compute effectively, very simply with some extra measurements, the excited state energies and properties. So this allowed us to actually go to the excited states, and so we actually have a very similar set of curves if you look at H2. But what we have done now is we actually added a couple of the excited states that are in this system. And what that allows us to do actually with the algorithm itself, it also seems to reduce the errors that we see in our algorithms. So we can get pretty close to chemical accuracy, which is about a kcal per mole. I would preferably go to a tenth of a kcal per mole, because a tenth of a kcal per mole is really where most of the kinetics happens. And that's where most of our real relevant processes are happening. So we need to go another order of magnitude lower to really get to the problems that are really interesting. What this also highlights is the challenge that you have when you have imperfect gates and qubits, and that they do introduce small errors, because you see that little word there, spurious state. We're actually starting to see some other states in that system that are not supposed to be there. So, and we're not the only ones that have done this. You saw the Google example. Here is, of course, the IBM example that came out earlier this year, where they actually have gone to a 3-atom system. Right now, we're looking at systems that are also at a similar size, but we're looking at potentially 8 to 10 atoms for the quantum computing problems we want to solve. We're not really interested in, again, calculating this potential energy service. We're actually switched to looking at what are chemical processes and chemical reactions and chemical properties that we would want to calculate with a quantum computer. So where can quantum chemistry go next when we get more qubits? So let's say the systems now are at 50 qubits. If you really look at this and do the math, we potentially could do something that is coronine. That is about 24 orbitals, as they call them, 24 electrons that we're interested in. If you want to do an exact calculation on that within a active space, a relevant space of the chemical problem, it's about 24 electrons and 24 orbitals, which means 48 spin orbitals, which is about 50 qubits that we would need. Now, interestingly, that largest one you can barely do on a supercomputer right now. It's about 1 trillion, what they call determinants. That means effectively you need 1 trillion elements to be stored in memory. So that gets pretty big. So why are these systems actually interesting? These are all pi conjugated systems, so they're important for photochemistry and photobiology. But these are also building blocks for functional nanomaterials and nano devices. So you could actually start functionalizing these and start looking at photo excitation and photo absorption. So thinking of ways to use this as solar capture. So what is Berkeley doing for quantum algorithms for the next 5 years? We're actually going to work on the dynamics of chemical systems. So we are able to do static properties, excited states, but we really a lot of our problems and a lot of our processes are driven by non-equilibrium behavior. Start to look at electron transport, response to external perturbations or driving forces. We're also doing some work on quantum machine learning, which is led out of Harvard by Asper Guzik. We'll be working a lot on the software stack with the vendors that are also developed their software stack and looking at optimizations and working on stochastic optimizations and actually also on linear algebra. So for dynamics, if you start to think about that, these problems become pretty big pretty quickly. So if you have a problem where you need not only look at the electronic states, but also, for example, at the nuclear degrees of motion. So the molecule is breathing, it's not standing still, and you want to couple those. Now you have to actually start looking at how you store those kind of vibrations into the system itself. The systems get very big very quickly, in the sense that if you do something that is 10 electrons and you do 10 vibrations, that's an exascale problem on its own. So we might be able to tackle that in 2021. But it requires an enormous amount of memory. So the interesting challenge here, of course, is that we have to somehow encode vibrational motions. We might be able to We had hoped initially to use the cavity modes when we were doing not flat architectures, but now everybody is moving to flat architectures, so those are not relevant approaches right now. So we have to actually find new ways to encode that kind of information. Just to close off, I wanted to mention a little bit about Berkeley Lab and how they actually do work extensively in industry. We're a Department of Energy lab, but we're really between universities and industry. So we're really tasked to bring basic science towards a point where industry can take it over. So Berkeley Lab works in a lot of different areas, and I'm not going to all mention them. My area is in computing sciences, and I work a lot with the experimentalists and the scientists in energy sciences. We actually have a lot of user facilities that commercial entities can get access to, such as the Advanced Light Source, NERSC, the supercomputing facility, the molecular foundry, and so on. Well, these are the 5 we have right now, and soon Berkeley Lab will have also a quantum testbed that can be accessed. And again, it's superconducting qubits that will be in the order of about 50 to 64 in the next couple of years. Okay. So how could you actually work with us? So there is actually an HPC for manufacturing program that has been looking at accelerating information for companies. But they have been really focused around around computational computing approaches, so helping you accelerate codes and actually use high-performance computing resources at the labs to do quantum computing. Now, actually, we can also offer quantum computing as a part of this program. And maybe very interesting, and I bring this up because a lot of people don't realize this yet, but Secretary of Energy Rick Perry actually announced a new way of developing partnerships, which is called the Agreement for Commercialization Technology, which is really an interesting change in the way labs normally work with industry. There's a lot more flexibility regarding intellectual property rights. There's also better alignment with industry regarding payments and indemnification, and it allows multi-party research and development. So especially I think the first one has been a long struggle for a lot of companies when it comes to intellectual property rights. So this might actually be resolved and make things easier for companies to start working with a national lab. So that's kind of what I wanted to talk about. Berkeley Lab is definitely a potential partner here for you guys to work on quantum computing. And I thank you for your attention.
So you talk about being able to calculate these excited states. Can you kind of give the industry what's the implications of being able to do this? And is this something that classical computing could not do easily?
So the question is, why are excited states interesting? If you really look around, everything you do is driven by excited state processes. So moving charge through a battery is often an excited state process. So I can expand on other examples, but solar cells is driven by excited state processes. So you can go through every chemical problem that a company has, and at least 75% are driven by excited state processes one way or another. If it's literally going into a physical excited state, or if you go into a vibrationally excited state. But they're all excited state processes. So why is this hard to do? Simply, you want to be able to get the electron correlation right. The electron correlation is what makes the exponential complexity and makes it very expensive to do computationally. I mentioned the 24, so the coronene example is really the limit of what we can do right now. What we want to do is the enzyme that does the nitrogen fixation or the nitrogen transformation. That is a problem that is more in the order of 50 orbitals, 50 electrons. So that's a problem that's twice as big, but given it's an exponential problem, is way bigger than we can do on a conventional computer right now. I didn't mention this, but I'll put it up there anyway. So one thing that we've started to look at using quantum computers for is also to develop theories. So right now, for academia or even the national labs, they're developing approximate methods so they can still compute the properties, the problems that they want to try and solve. Well, we don't know how good our theories are. So even quantum computers can have a completely different function. They can serve potentially also as a benchmark of an exact solution that we can try develop theories against. So that might be another way to start using quantum computers in the future.
Somewhat related to what you said. You mentioned two approaches to simulation, quantum computing simulation of chemistry. One kind of the computational, and one is more like analog computing in some sense. Now, are the hardware challenges similar in both camps, or are there something specifically more difficult or easier in the analog approach?
To me, thinking about the digital approach, where we actually just enumerate the number of possibilities that we would have, is easier to think about. If you would want to do the real analog computing and effectively take each qubit and describe an atom, you're not interested in 2 states in an atom. You would be interested in many more states. So we're talking about qubits. In reality, we would like to be qubits, the higher order qubits. We want to be able to potentially access higher levels and higher states if you really want to do more of an analog simulation, actually start to probe the real chemistry and physics. Because again, most of these processes don't happen on that lowest 1 or 2 states. They happen on higher level states where they move across potential energy surfaces.